Hi everyone, I'm really happy about the involvement of the class in this proposal number 3. Some short explanations follow. Then data extraction is simple. We have the heat exchanger table, some data about economics, and we can get the minimum temperature approach from the process-to-process heat exchangers in this table. Minimum approach is 21 Celsius, but you see we have not taken into account some smaller approach in a cooler like this 17 Celsius in heat exchanger 8. From the heat exchanger table we can derive the process, hot streams and cold streams, and the utilities, the heating utilities in every heat exchanger. And also we can sum up the utilities by type. With the process hot and cold stream and using 21 as minimum approach, we can calculate the composite curves. These composite curves give us 39 megawatts as minimum heating and 65.99 megawatts of cooling. This is for 21 Celsius minimum approach, but if you try with highest minimum approach till 61, the minimum utilities are the same. Then, comparing the current utilities with the minimum utilities, we can calculate an excess of 3.15 megawatts. This is 7.4% in heating and 4.6% in cooling. It can seem not very wide, but as heat flows are big, then savings can be big also. I have then made the proposal of new utilities. Not using 9 bar G steam heating and trying to generate as much steam as possible. For this steam generator, I have used also the preheating part of the stream. How much preheating is needed for every kilogram per second of steam are in the economic data. These 340 kilojoules per 2015 kilojoules of vaporization enthalpy. Then with this relation you can calculate how much preheating you need for a concrete complete enthalpy flow. I have also included as much air cooling as possible and the rest as cooling water. I have included also a fake 14 to 14 cooling water stream in order to meet this 21 Celsius minimum approach that we need for calculating. As you can see, this is small, 660 kilowatts in comparison with the whole amount of cooling water. These calculations have been done using the combined composite curve and trying an error. But this is more simple using the grand composite curve, as we will learn in the near future. I have also changed the temperature of the flue gases in the boiler, not change of the enthalpy flow, but with that final temperature we can have an idea on how much natural gas or fuel we can need. With this result we can make some numbers about the cost of the new utilities, and we find a reduction of 15%, which is a significant one. and the absolute amount of savings is almost 850,000 Canadian dollar per year. Finally, for calculating the minimum number of units, I have divided the problem in 4 zones, separated by the utility pins we have created using as much utility of each type as possible. These give us 4 different zones, and looking at the population of a stream in every zone, we can calculate the chunks or complete stream in every zone, and minus 1, the whole summation gives us 31 minimum number of heat exchanger. See that the current number of units is smaller, is 18. This is probably due to the excessive using of utility up the minimum. Okay, this is just my solution. This is an open-end problem. Then many solutions can be considered as correct. And that's all. Good work.